Okay, so we'll begin the session. Welcome back to the weekly live tutorial sessions on wheel mobile robots. I am Isaac John. I am a PhD scholar from IIT Palakkad. So far we have we were covering the mechanics of wheel mobile robots. So until week two, we have covered all the topics, including kinematics of wheel mobile robots. In the previous week, we have also seen, how to model the kinematics of different configurations of mobile robot base. For example, like we have seen multiple cases, including a basic two-wheel differential drive. We have seen the case of a differential, a skid steering. We have seen mobile robot configurations with unconventional wheels. Two of them are, the one with the four mechanism wheels and the one with three omni wheels. We have also seen a formulation where we can actually derive a generalized wheel metrics for all these different configurations, so that we can appropriately model or simulate the kinematics of various mobile bases. So this week we are actually getting on to the dynamics of wheel mobile robots. So this would be this would basically cover the mechanics part of wheel mobile robots, and from the subsequent weeks we'll look into navigation, path planning, and various sensors, and further on we will discuss design of motion controllers. But before that, let us get on with our current session, which we would be dealing with dynamics. So for today's presentation, I would like to give a brief overview about robot dynamics. What are the problems that we are usually interested to solve in robot dynamics, and how do we derive the equations of motion, or the governing equations of motion of a mobile robot. We can basically use two principles. The first being an Euler-Lagrange method. It's based on energy principle, and the second one is actually a Newton-Euler method, which is derived actually from the momentum principles, impulse momentum principles. And then later on, just like how we have derived the wheel configuration metrics for different mobile robots in kinematics, we will also see the dynamic models of various configurations of wheel mobile robots, having different wheel configurations, such as differential wheel, skid steering, four wheel mechanical drive, so on and so forth. Before that, let us have a brief overview of the things that we wanted to solve, or what basically dynamics means and how it translates. So basically, dynamics is nothing but a study of systems that undergo changes of state as time evolves. So like a mobile robotic system, or any robotic manipulators, whatever in that matter, we wanted to see how the system's states changes as time evolves. If it is acted on by an external forces, or if it is acted on by some external unbalanced forces, such as the inputs that we give through the motors. We would like to see how the system evolves as time progresses. For example, like if you drive all the wheels of a differential wheel robot, with a constant torque, uh, we expect the mobile robot to move forward, right? If all the inputs are the same, are of the same magnitude, and are of the same direction, we expect the differential wheel drive to move forward. So basically, dynamics basically covers how the system's state basically changes as time occurs. And depending on the system, the state of the system, we can use different variables or different parameters to define the state of a system. It could be you could define the state in terms of positions, velocities, and accelerations when we talk about a robotic system. Or if it is any other dynamical system, maybe an electrical system or maybe an RLC circuit, the parameters could be different. And when we when we talk about robotics, the change of state involves motion. So the state can be characterized by the parameters that defines motion. Which are which could be the position coordinates, its derivatives, which is the velocities, and its derivative, which is the acceleration. And basically, in dynamics, why and how the motion occurs when the forces and moments are applied on the bodies. So that is the fundamental problem that we are actually trying to understand. If a force or if a moment is applied on the actuators, or the forces need not necessarily constrain itself within the actuators, and it could act on the mobile robot. It could act externally as well. Any sort of interaction that the mobile robot has with the environment, and how it affects the state of the robot. The state basically means the motion. All these things is what we are trying to find out using dynamics. And for that, what basically defines the dynamics of a mobile robotic system are its equations of motion, right? So deriving this equation of motion is essential to understand how the systems or how the mobile robot states evolves with respect to time. And deriving this is basically essential in design, analysis, and control of the system, correct? So in case of design, how it basically uh, uh, contributes is, like, if you want the mobile robot to move in a specific direction with the specific velocities and accelerations, how much forces or how much torque should we apply on the actuators, right? So those sort of problems is actually a design problem. If our robotic system is to have a specific minimal velocity, we want the robotic system to move with minimal velocity, it'll be subjected to increased forces. We'll have to apply increased torque through the shafts. So the shafts and all those things will have to be designed so that the increased amount of torque can be accommodated. So that makes it a design problem. And analysis basically means, it's basically how you simulate a mobile robotic system. Like, for example, if you give so and so torques onto the robot's actuators, how does the robot move, or how does the wheel mobile robot move? So we can basically gain that sort of insights from this equations of motion, or from the governing equations of motion, right? So like, if you plug in the inputs, uh, the inputs being the torques that we are supplying on the motors, the governing equations basically give you insights on how the robot moves, or how the robot follows a trajectory. And then control. The governing equations of motion also facilitates controlling the robot. Like, for example, if you want a robot to move a specific path, right? We do not want our robot to veer away from this path. We want our robot to closely follow this trajectory, our desired trajectory. And to bring our robot, or to maintain that stable trajectory throughout its operating period, we have to basically we should essentially know the governing equations of the mobile robot. Then only we can able to supply the adequate amount of torques, or we can basically plan how much inputs we should be giving to the actuators. Then we'll talk more about equations of motion. So the way in which the motion of the robotic system arises from torques or forces applied by the actuators, or from external forces, moments applied to the system, right? So it's basically a mathematical representation of a mobile robot. For example, if you consider this to be a mobile robot, I'll attach a body fixed frame of reference, XB, YB, right? And it is subjected to some inputs. I'll denote these as the wheels of a mobile robot, like so. So the inputs being the torques that we are giving to the wheels. So by convention, we'll stick this as wheel one, we'll stick this as wheel two, and this tau 1 and tau 2 are basically nothing but the torques that we apply to the wheels. And it could also be subjected to some external forces, probably Fx, Fy, M, and a moment, Mz. So if these are the forces or forces and moments, we call them wrenches, as a collective term. Uh, the equations of motion or the governing equations of motion basically decide how this robot reacts or how the mobile robot responds to this set of inputs, right? In a mathematical sense. So that is why it is really essential to to estimate or to understand or to derive the governing equations of motion, so that it will basically give you uh, a lot of insights on how a mobile robot would respond to a specific set of inputs, and those could be used for design, analysis and control of the system. All right. So just like what we have seen in kinematics, dynamics also has two important problems. The first being forward dynamics, and the second being inverse dynamics, right? So it's more or less analogous to the kinematic problem that we have seen, the inverse and forward kinematic problems. So suppose we have, a mobile robot like so. I'll represent this mobile robot using this governing equation, as a function of, uh, or you can actually give this tau as a function of eta dot and eta double dot, right? And if you are giving a control input torque, right? If you consider this to be the inputs, the forces and the moments, and the outputs as the trajectory, eta dot, eta double dot. So this problem is basically the forward dynamics problem. How a robot would respond for a given set of inputs, and the response can be characterized by the trajectory coordinates, position, velocities, and accelerations. So that's what it basically says. For a given input vector tau, calculate the resulting motion of the robot characterized by eta dot, and eta double dot. So this is analogous to a problem of simulating or analyzing the robot in a mathematical sense, right? If you have a computer in front of you, you can basically write a mathematical program that represents the dynamics of the system, like so. So you'll have a mathematical representation of a mobile robot, and if you supply the inputs, the inputs being the torque to the motors, how will your mathematical model respond? How will it move? Will it move in a straight manner? Will it move in a curved manner? Will it move laterally? Will it move diagonally? All these sort of things can be obtained by the forward dynamics problem. Whereas in case of inverse dynamics, we go the other way. We define the trajectory of the mobile robot first. For example, that is more relevant to an actual problem, right? We want our mobile robot to follow a desired trajectory, right? We want the mobile robot to go through a set of points with a prescribed velocity. So if you want a mobile robot to go through a desired point, what should be the control inputs that we should be giving to the motors, so that the mobile robot can realize that set trajectory. So that problem is basically inverse dynamics. So for a given desired trajectory, eta dot, and eta double dot, find the required input vector tau. So basically, by giving this input torque vector, we are basically trying to control the motion of a mobile robot along our desired trajectory. So it's akin to, or it's analogous to, the problem of controlling the mobile robot, right? Whereas in the case of forward dynamics, it's a problem of simulating the mobile robot, and in case of an inverse dynamics problem, it's basically akin to controlling the mobile robot. Okay, so yeah, that's about it. And now we will go on to how we derive these equations of motion, or how to have a mathematical representation of the behavior of a mobile robot. So like we can do this by two principles. The first being the Euler-Lagrange method. So it basically says, it basically says you can derive this expression, the Stark expression as the function of the trajectory coordinates using using this for using this following equation. So this is nothing but you take the partial derivative of this scalar called Lagrangian with respect to the vector of velocity coordinates, and then you take the derivative of it with respect to time, and then you subtract it with this term, dou L by dou theta. So like I hope you can recall what this theta is basically. Theta is nothing but the vector of velocity coordinates UVR with respect to the body fixed frame of reference. So if you consider this to be the body fixed frame of reference, P, and this is the XB axis and this is the YB axis, right? So the velocity along the body fixed XB axis is nothing but U, and the linear velocity along the body fixed YB axis is V, and the angular velocity with respect to the ZB axis, is R. Then the vector zeta is nothing but a vector of UVR, right? And this tau is also a vector. If you expand this, the tau is nothing but Fx, Fy, and Mz, right? Which is nothing but the force along XB axis, that is Fx, and Fy is nothing but the force along YB axis, and Mz is nothing but the moment, the resulting moment about the net moment about the ZB axis. So this is basically a vector equation, right? Because theta is a vector, theta dot is a vector, and theta is a vector. So you will have to basically write this equation, or you have to basically expand this equation 3 times so that you will be able to get each of these components, right? So you will have to first Fx would be, so in that regard, Fx would be nothing but d by dt of dou L by dou u dot multiplied by dou L by dou u. So that is Fx, and similarly Fy would be d by dt of dou L by dou v dot minus dou L by dou v. Right? And similarly, Mz also, instead of u dot and v dot, it will be r dot, and instead of u or v, it will be r. And then we haven't yet defined what this Lagrangian means. It's what the scalar L means. So for any given dynamical system or for any robotic system, this Lagrangian is defined as the difference between the kinetic energy and the potential energy. Difference between Ke and Pe. So yeah, this is how we basically define the kinetic energy. So what do we have? So we have defined a mobile base like so, and we have also attached a body fixed frame of reference, XB and YB, and you can assume this red blob on this figure, C, as the center of mass. This, you can assume this to be where the mass seem to be concentrated, because it necessarily need not be concentrated at the at the geometrical center, because practically it's almost impossible to have the center of mass to be located exactly at the exactly at this geometrical center, because uh, most often the mobile robot would not have any sort of symmetry, because once you mount the sensors, actuators, and all those things, there will be some shift in the center of gravity. So like you can arbitrarily assume the center of gravity to be at a coordinate, xb, xbc, and ybc. This one, xbc and ybc from this body fixed frame of reference, right? XBC distance from the YB axis and YBC distance from the XB axis. right? And m is basically the center of mass or the total mass of the mobile robot, concentrated at this point C. And ICZ is basically the moment of inertia with respect to the ZB axis, the polar moment of inertia with respect to this ZB axis. So then, how do you define the kinetic energy of this system? So kinetic energy of this mass, the kinetic energy of this mass is nothing but half mv square, half mvc square, because of that linear velocity component plus half ICZ r square. This is nothing but the total kinetic energy of the wheel mobile robot. But then how do you define this VC? So VC is nothing but, XC dot square plus YC dot square. This is nothing but VC, right? Because XC is basically the XC dot is nothing but the linear velocity of point C along x-axis, and YC is nothing but the linear velocity of point C with respect to y-axis, and the resultant of XC and YC will give you this total resultant velocity VC. Now the question comes, what exactly is this XC and YC? You already know that the wheel mobile robot has its own velocity, its own linear velocity u along xb axis and v along yb axis and r with respect to zb axis. It has a base velocity u and v, and due to the rotation, it will also have a second component. So if due to this rotation, it will have this omega cross r component, right? So what is that component? So if you write that vectorially, omega is nothing but this r. R is nothing but the angular velocity cross the position vector. The position vector to this point C is nothing but x c I cap plus y c j cap. Right. So if you expand this, what will you get? You will get, so r is along k, the k unit vector. So if you expand this, you will get xc or xbc. I have used xbc in the convention. xbcr, k cross I is j, positive j, and k cross j is minus I, minus ybc r I cap. Right? So the total velocity, the total velocity along xb axis is nothing but u minus ybc r I cap, and the total velocity, or you can call this as xbc dot. And similarly, ybc dot is v plus xbc r. This is actually j cap. Right? So to find the resultant linear velocity, so Vc is nothing but, or Vc square is nothing but x bc dot square plus ybc dot square. Right? So if you square and add these two components, you will get the Vc square, and then you can basically substitute into this equation of kinetic energy. And similarly, you can carry over this term as well. So you have essentially derived the kinetic energy of this equation, right? And then what about the potential energy? Because we have defined this Lagrangian to be the difference between kinetic energy and potential energy, and we have basically described how to derive this kinetic energy. But how do we derive this potential energy? So in fact, in case of a mobile robot, you can basically disregard potential energy because this is a planar robot, right? So the entire mobile robot operates in a constant plane throughout. So if you consider that plane of operation as a datum or the reference plane, you can fix the potential energy to be zero. So irrespective of how the mobile robot moves within that plane, the potential energy is not going to change. It's always going to be zero. But that's not the case for a spatial robot, that can move within different planes, or in case of a robotic manipulator, which can move in space. But in case of a planar mobile robot, fix the datum of you can fix the datum as the plane of that mobile robot itself, and due to that, you can basically consider the potential energy to be zero. So, with that, the Lagrangian basically becomes the kinetic energy itself. And once you do this operation component by component wise, you will get these equations of motion like so. The first equation or the net force along x direction is m u dot minus mr dot by dc minus uh, mr by dc dot. And the net force along y-axis is mv dot plus mr dot xbc plus mr xbc dot. And the moment, about z-axis. The two relevant forces and the one relevant moment can be derived as such. By taking the partial derivative with respect to the velocity coordinates and then taking the total derivative with respect to the time. So you can basically derive the equations or the governing equations of motion like so. Yeah. So yeah, that's about it actually. Use on deriving the equations of motion using this Euler-Lagrange method. So you basically expand this xbc dot and ybc dot, and then substitute into this VC equation, and then you carry forward these operations. And as a result, you will get these three resulting governing equations of motion, Fx, Fi, and Mz, which correlates, the trajectories or which coordinates the position, the motion parameters, which is the acceleration, the velocities, and the position coordinates to the forces. Another approach what we do is deriving the same equations of motion using the principles of impulse and momentum. So this is basically what we call a Newton-Euler method. So it's much more involved. It's much more comprehensive than the Newton-Euler approach. And the reason that we go with the Newton-Euler approach is that it gives you much more insights, or it gives you much more insights. So, like for example, earlier in case of Euler-Lagrange method, you only got the forces in Fx, Fi, and Mz, right? Because it's a mobile robot that basically lives in a plane. Other coordinates are not relevant. But the difference in formulation becomes much more relevant in manipulators, right? In manipulators, the Euler-Lagrange method would only give you the joint torques, but Newton-Euler method gives you much more comprehensive insights. Apart from the torques, it will give you the torques or the reaction forces in all the other directions. Right. So that is actually really useful if you are designing the links of the mechanism. Right. So only one component would be counted as this actuation forces. Right. For example, if you have a revolute joint like this, you basically actuate this revolute joint with respect to a single axis, which is nothing but the axis of the revolute joint. And all the other all the other component. Like for example, if you consider this to be the z-axis, and you can have you can have other axes. Probably you can call this x-axis, and maybe you can call this y-axis. You only actuate the revolute joint with respect to z-axis, right? You only give the command with respect to z-axis, the torque. So Euler-Lagrange is actually very good in only giving you this information. It will filter out the other reaction forces. So like if you have multiple such revolute joints, Euler-Lagrange would only give you that relevant thoughts only about z-axis of all the other joints. But then if you are interested to design a robotic manipulator or a mobile robot, you would also want to know the reaction forces in other directions also. Not along the axis of actuation, but other axes. There could be force. Sorry, there could be there could be reaction forces along x-axis. I'll call this Rx. There could be reaction forces along Ry. There could be reaction moments about x-axis, mx, reaction moments about my, and you can also have reaction force along the axis of the revolute joint, Fz. All these things you can actually obtain, if you go with this Newton-Euler approach. And then we can actually select the relevant axes, or we can select the relevant coordinates to see, how much torque that we are required to give. So to derive the equations of motion using this Euler-Lagrange, we first begin by deriving the expressions for position coordinates. Then we take the derivative of that with respect to time to get the velocity expressions. And then we finally take one more derivative with respect to time to get the acceleration coordinates. So like once we have these acceleration coordinates, then it is much more straightforward, to find the relationship between all the forces acting and the accelerations. So if I define a ground fixed inertial frame of reference, I'll label this as frame I. If these are the inertial coordinates, xi and yi, right? And if you consider this red blob to be the center of mass, I would define a position vector like so from the inertial frame of reference. So the position vector, if I label this, I shall call this position vector of C, point C with respect to this inertial frame. And I would also define a position vector to the origin of this body fixed frame of reference B, right? So I would represent this position vector as position vector of B with respect to I, position vector of origin of the body fixed frame with respect to I, and one more frame of reference, like so. So I'll call this position vector of point C with respect to B, right? Because this point C can be easily defined with respect to the frame of reference B. Because, irrespective of how the mobile robot moves, the body fixed frame also moves with it. So that the coordinate of C with respect to B is always going to be fixed. It's for all periods of time, it's always going to be the same. So if I write this vector loop equation, how would it look like? We can write this vector equation like so. So this position vector of the position vector of C with respect to I is nothing but position vector of B with respect to I plus position vector of C with respect to I, right? Because if you are writing a vectorial equation, all the position coordinates should be referred with respect to a single frame of reference. But if you have noticed here, we have already established that it is much more convenient to represent the position coordinate of C with respect to B. That's what we have, right? It's a static quantity, it's a constant, or it's a fixed quantity. But this will always be different. If the mobile robot goes someplace else, this quantity is going to change. So what we can do is that we can basically write it as position vector of C with respect to B, and then using a rotation matrix, we can bring it to frame I. Rotation matrix of B with respect to I, right? Where this rotation matrix basically, defines the orientation of this body fixed frame B with respect to the initial frame I, right? So I'll label this as equation 1. So that is about the position coordinates. So to get the velocities, we'll have to differentiate this equation 1 with respect to time. So differentiating equation 1 with respect to time, we will get, position vector of C with respect to I, dot. Dot basically is used to denote that it's, we are differentiating that with respect to time. Then we'll apply it throughout, position vector of B with respect to I plus, and for the second term, we'll have to apply the chain rule or the product rule, right? So that makes it IRB dot BPC plus IRB BPC dot. So I label this as equation 2. So, okay, so then how can we further proceed from this? So like we have already mentioned that the position vector of C with respect to B, right? This one is always going to be constant, right? Because the position vector is defined with respect to frame B, and no matter how the mobile robot moves, the frame B, since it is attached to the mobile robot, this vector is always going to be constant. So the derivative of that with respect to time, BPC dot, this is going to be 0 since it's a constant vector. So this becomes 0. So yeah, so we can basically, that's how we establish that. Then how do we define this, the derivative of this rotation matrix? How do we define that? So what is this? What is the derivative of this rotation matrix? So we can follow this by considering the fact that the rotation matrix is an orthonormal matrix, right? You know how the rotation matrix would look like, right? It's like cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. Where theta is basically the orientation between the body fixed frame of reference and the inertial frame of reference, right? So this is actually an orthonormal matrix, right? Because, if you take the norm of each of these columns, they are 1, right? Cos square theta plus sine square theta plus 0 square is 1. Minus sine square theta plus cos square theta plus 0 square is 1. Then 0 square plus 0 square plus 1 square is 1. So like all the length of all the columns is 1. And if you call this as the rotation matrix R, then R transpose is also its inverse. And that makes this matrix an orthonormal matrix, right? It's the norm of this matrix is 1, and the transpose of that matrix is also its inverse. So from this fact, we can basically write this equation. R transpose is an identity matrix, right? I'll call this equation A, right? Because we know a matrix for any general matrix, A inverse is going to be identity matrix. But since so that applies to a rotation matrix also, right? R inverse is I. But since our rotational matrix is an orthonormal matrix, R inverse is also R transpose, right? So if I replace this R transpose, R inverse with R transpose, it's equivalent to this identity matrix. So that's what I have written in this equation A, right? So if I take the derivative of equation A, differentiating equation A with respect to time, again, you will have to apply this product rule. So I'll write it as R dot R transpose plus R dot transpose, and the right hand side is going to be 0, right? Because identity matrix is a constant matrix, and the time derivative of a constant matrix is obviously 0. So now what I'll do is I'll rewrite this second term, right? I'll write that second term as R dot R transpose, the whole transpose. And I'll simply carry forward the first term, R dot R transpose, right? Because if you take the transpose of this whole thing inside this parenthesis, you will get back the previous step, right? It's from the basic identity that, A, B, the whole transpose is V transpose A transpose, right? So if you apply that, if you take the transpose of this thing, you will get it as R R dot transpose. That is nothing but this term, right? So I hope we are clear up to this step. So what can you infer from this step? The thing here, R dot R transpose and R dot R transpose, the whole transpose is 0, right? So what does this infer? So if I call this R dot R transpose as a matrix A, we have an identity A plus A transpose is 0. So if a sum of a matrix and its transpose is 0, that means that this matrix A is a skew-symmetric matrix, right? Or if we apply that, R dot R transpose is a skew-symmetric matrix, going by that. So this implies R dot R transpose is S. This is nothing but a skew-symmetric matrix. Write it like this. It's a skew-symmetric matrix. So then what exactly is this R dot R transpose? So a typical R matrix for a mobile robot would look something like this, right? R matrix would look something like, cos theta minus sine theta 0, then then sine theta cos theta 0, then we have 0, 0, 1. So this is how a typical rotation matrix for a mobile robot would look like, right? Then how would R dot would look like? So that is the case, then R dot, you have to take the derivative of each of these components within this R matrix. So that makes it minus sine theta dot minus cos theta dot 0, then cos theta dot minus sine theta dot 0, then 0, 0, 0. Right? So if that is the case, then how would this R dot R transpose would look like? We have R dot, we have R, then we can basically multiply both of them to see, how this R dot R transpose would look like. We expect a skew-symmetric matrix, right? Let's see if that is the case. So I'll write R dot R transpose as minus sine theta theta dot minus cos theta theta dot 0, then cos theta theta dot minus sine theta theta dot 0, then 0, 0, 0. Then we have to multiply this with R transpose, so that makes it cos theta minus sine theta 0, sine theta cos theta 0, then 0, 0, 1. So if we expand this, what will you get? If you expand that out, you will get it as minus sine theta cos theta theta dot plus cos theta sine theta theta dot. So that makes it 0. So like ultimately you will end up with something like this, 0 minus theta dot 0, theta dot 0, 0, 0, 0, 0. And this is your skew symmetric matrix. This is how that skew symmetric matrix would look like. This term, right? So, in a general sense, if the rotation occurs in 3 dimensions, right? If the rotation occurs in 3 dimensions, you will have this angular velocity vector like omega x, omega y, and omega z. And the skew symmetric matrix would look something like this. All the diagonal elements of a skew symmetric matrix is going to be 0. Then the remaining elements would look something like this: omega x minus omega y, omega z. So this becomes minus omega z, omega y minus omega x. This is how the skew symmetric matrix would look like for a general case of 3-dimensional rotation. But since our rotation is about only a single plane or about a single axis, omega x and omega y components are non-existent, and the only component that exists is basically omega z, because the rotation is only about the z axis. So by our convention, omega z is nothing but r. Omega z is nothing but the angular velocity of the mobile robot about zb axis, and that is, from our convention, we use this symbol r to denote that component. So our skew symmetric matrix from a mobile robot's point of view would look something like this. All the diagonal entries are still 0, but the entry corresponding to omega z is non-zero. So this becomes theta. This becomes r, and this becomes minus r. Okay, so now that we have established that case, r dot, what was that? R transpose is a skew symmetric matrix. Then what is r dot? Because that is what we originally wanted to find out, right? This is what we originally intend to find. What is this r dot? So we can find it by multiplying or post-multiplying the skew symmetric matrix with, the inverse of this transpose. So r dot is nothing but S multiplied by R, right? If you take the transpose, if you take the inverse of this transpose, inverse and transpose is equal for a rotation matrix. So it becomes R transpose transpose or R inverse inverse. So that makes it R. So we know what the constituent elements of this S matrix. We know what this R is. So that makes R dot is nothing but S cross R. So yeah, if once we have obtained that inference, we can basically go back to equation 2, and we can replace this R dot by this SR, right? So yeah, I'll reproduce that equation 2 one more time. So equation 2 was nothing but uh, IPC dot is position vector of B with respect to I dot plus IRB dot BPC, right? So instead of this IRB dot, I'll replace this with this term, SR. So instead of this S, I'll use this omega matrix, omega instead of this, because it's a vector of angular velocity. So I write it as, I'll write it as IPB dot plus this omega. It's a matrix though, multiplied by the rotation matrix B with respect to I. So this is nothing but this SR. Then we have this term remaining, BPC. So I'll call this as equation 3. So, another thing that I would like to bring to your attention is that, for a general cross product, for example, if you consider this general equation as V as omega cross R, you would know how to, take the cross product of two vectors. You would take the determinant of this matrix, ijk, omega x, omega y, omega z. Then you will have this rx, ry, rz. If you take the determinant of this matrix, you will basically get the expression of the linear velocity. This is how you take the cross product. You can also do a different operation which will give you the same result. So that is that can be defined by a matrix and a vector multiplication. So here I'll define a new matrix omega, and I'll simply multiply it with this R vector. And this omega vector can be a skew symmetric matrix. The diagonal elements are all 0, and the remaining elements are omega x minus omega y, omega z. This becomes minus omega z, omega y minus omega x. So this is a skew symmetric matrix. And if you multiply this with Rx, Ry, Rz, these are basically equivalent, right? Cross product of two vectors can also be expressed by, a matrix, multiplication of a skew symmetric matrix and the vector, the second vector. These are equivalent. You can expand both out and verify it yourself. And as a result, I can basically write this expression. This expression is similar to what we have written here. So I can replace this thing by an equivalent representation. Right? I can write this using a representation. Instead of writing this omega b as a skew symmetric matrix, I can write this omega b as a vector. So if I do that, this will become omega bi cross, right? If this is a pure vector. So that becomes our equation 3. Now I'll do one more transformation. So what exactly this is this? The derivative of the position vector of frame B with respect to I. That is nothing but the velocity of body fixed frame of reference, right? So I'll write it as velocity of B with respect to I plus I'll pre-multiply this term with the rotation matrices like so. B with respect to I multiplied by rotation matrix of I with respect to B, then I'll write the remaining terms, I omega B cross ARB multiplied by BPC. I'll call this equation 4, right? So essentially, these are equivalent. The only change I have made is, I have multiplied the second term with these two things. The rotation matrix, and this is the inverse or the transpose of the rotation matrix. And since these are inverses, the product of these two matrices is essentially an identity matrix. So it does not change this equation. It's just an identity matrix. So what I will do is that I will take this IRB common from all of these terms. So because I can also write this term as the velocity of frame B with respect to B, and I pre-multiply this with the rotation matrix IRB, because these are essentially equivalent. So like I'll take this rotation matrix common from all of these terms. What will I get? So I'll take it as common. IPC dot is nothing but IRB. If I take it as a common, then I'll get it as velocity of B. So since we are representing velocity of frame B with respect to its own frame of reference rather than ith frame, we don't have to write this superscript anymore. We can write it just like this, VB plus, we have taken this term common, and this term becomes omega B referred with respect to its frame of reference, right? Since we are pre-multiplying it with the rotation matrix, B Ri multiplied by I omega B is B omega B. The angular velocity of frame B with respect to its frame of reference. So we don't have to use this superscript anymore. Then this term will also come out. Then we multiply this with VPC. So I'll call this as equation 5. Right? So this is the expression for velocities. Right? And if you differentiate this once more, you will get the expression for accelerations. So I'll write it here, differentiating again. Once more, you will have to again apply some more product rule. So you'll get something like this. Position vector of C with respect to I double dot is, you will have to apply this product rule. So I RB multiplied by VB dot plus omega B dot cross BPC plus omega B cross BPC dot plus IRB dot multiplied by VB plus omega B cross BPC. So just like earlier, we know that this term is essentially 0, right? Because position vector of C with respect to B is always going to be a constant vector. So the derivative of that is going to be 0. So I'll just mark this term to be 0. And we know what the derivative of this is, IRB dot. That is nothing but, this is nothing but omega B, I omega B cross the rotation matrix of B with respect to I. That is what we have proved earlier. So making that substitution, so if I write it again, so you will get the subsequent expressions as IRB multiplied by VB dot plus omega B dot cross BPC plus I omega B cross IRB multiplied by VB plus omega B cross BPC. So just like what we did in the previous case, I'll just pre-multiply with, pre-multiply the second term with an identity matrix because it does not make any difference. So I'll pre-multiply it, and that makes it something like this. IRB multiplied by BRI. So this is essentially an identity matrix, so that sort of operation will not make any difference. But what we can do is that we can essentially take all these IRBs outside the bracket. So that makes it use a different ink. IPC double dot is IRB taken out. Then this VB dot, the derivative of this velocity of frame B with respect to its own frame of reference, I'll mark it as AB, acceleration, plus the derivative of angular velocity is nothing but angular acceleration, alpha B cross BPC. Then we will have the remaining terms, right? If I take one of these IRBs outside, this term would make it as omega B expressed with respect to its frame of reference, omega B cross, we'll have to expand it out, VB plus omega B cross omega B cross BPC, right? And the double derivative of position vector of C with respect to I can write it as acceleration of point C with respect to I, right? I can also write this equivalently as acceleration of point C with respect to B multiplied by the rotation matrix, acceleration of B with respect to I, because these are equivalent. So what happens is that this IRB and this IRB gets cancelled. So at the end, we'll get the expression of the acceleration of the point C with respect to the body frame as AB plus alpha B cross BPC plus omega B cross VB plus omega B cross omega B cross BPC. Right? This is the expression for the acceleration of point C with respect to the body fixed frame of reference. Right? So if I substitute the corresponding symbols, I'll write this AB as U dot, V dot, R dot, or I'll just write the linear part, the linear part. So AB can be considered as U dot, V dot, and alpha B is nothing but R, it's 0, 0, R dot. This cross BPC. BPC is the position vector of point C with respect to frame B. So that is given by XBC and YBC, right? So this cross XBC, YBC, 0 plus omega B is nothing but 0, 0, R. This multiplied by VB. VB is the velocity of the robot with respect to its body fixed frame of reference. That is nothing but U and V. So I'll label this as U, V, 0 plus omega B cross BPC. So that something but 0, 0, R cross 0, 0, R cross XBC, YBC 0. This could be a linear. You can consider the Z a linear component to be 0 because it's a planar mechanism. So yeah, what are those? What are these terms? We will basically expand, one or two of these terms just to be more clear. So the first term, alpha B cross BPC, or this term, if I wanted to expand it, alpha B cross BPC, if I can expand it as if I take the determinant of this matrix, you will get the expression for that 0, 0, R dot XBC, YBC 0. So if I take the determinant of it, I'll probably get it as, minus YR dot I cap plus XR dot J cap. So that was this term. And if I expand this term, I'll get it as omega B cross BB as the determinant of IJK multiplied by 0, 0, R multiplied by UV0. So if I expand this out, I'll get it as minus VRI cap plus URJ cap. Then what do we have? We have this term as well, omega B cross omega B cross, omega B cross BPC. So if I expand that out, omega B, I'll give the final expression, omega B cross BPC. The final expression would look like minus X BC R square I cap minus YBC R square J cap. Right? So then what makes you, then if you substitute everything, then if you can substitute everything, BAC as U dot V dot 0 plus minus YR dot XR dot 0 plus minus VR UR 0 plus minus XR minus minus XBC R square minus YBC R square 0. So this is nothing but BAC is nothing but Fx, Fy, Fz. And as you can see, Fz is all the entries of Fz are all 0 because it's a planar mechanism and the only net forces acting are on Fx and Fy, and we only have a moment about the Z axis. So if you multiply this with the mass, the total mass, you will get the expression for Fx. The first component would be something like this, mu dot minus my r dot minus mvr minus mxbc r square, and fy would be mv dot plus mybc xbc r dot plus mur minus mybc r square. And I can write it like in a matrix and a vector form. So I'll write it as fx, fy. Fz is going to be 0 because it's a planar mechanism. And if I write it like this, u dot, v dot, and r dot, these are the vector of accelerations. And this matrix, what we are about to fill, we call this as the mass matrix. So if I segregate everything into a mass matrix, you will get it as m u dot. Then the other term is 0. Then coefficient of r dot is minus m YBC. And similarly, for the second entry, it's 0, M, and M XBC plus M XBC. And all the other remaining terms, you can collect it into a vector, minus M R V plus XBC R. And the other term is, second term is MR U minus YBC R. So going back, you have basically obtained the expression for the acceleration along x-axis and acceleration along y-axis. And if you take the resulting moment about, the body fixed frame of reference, because this force, this inertial force will have a moment about this axis. And this inertial force, the component of this inertial force will also have a moment about, ZB axis. And there is also moment contributed by this ICZ component, ICZ multiplied by R dot. Right. So if you take the resultant moment, the resultant of all the moment about the ZB axis, you will get the final expression for MZ like so. Right. The first two entries are we have obtained using this Newton-Euler method, and the final expression is nothing but taking the moments of all the resultant moments with respect to ZB axis. And as a result, you can represent this governing equations of motion using this compact matrix and vector form, where this D is nothing but the mass matrix, which is this one. This is a symmetric matrix. And zeta dot is a vector of accelerations with respect to the body fixed frame of reference. That is this vector, u dot v dot r dot. And this vector is nothing but, you can call this as a vector of, centrifugal and Coriolis effects. Okay, right. So yeah, we have derived this entire equations of motion with respect to the body fixed frame of reference. Right? These are nothing but the velocities with respect to the body fixed frame of reference. But sometimes we would like to have we would like to derive this entire equations of motion with respect to the inertial frame of reference. Right? So then how do we do that? We do that using the conservation of power. So it basically says the power to move the robot at inertial frame of reference is equal to the power to move the robot at the body frame of reference. Right? Because power is a scalar quantity. So if you define the power in inertial frame of reference, and if you define the power in body fixed frame of reference, since it's a scalar, its magnitude is going to be the same. So it does not matter. Power is always going to be the same, irrespective of whether it is mentioned in inertial frame of reference or if it is mentioned with respect to the body fixed frame of reference. Right? So power is nothing but the force or the wrench multiplied by the velocities. So this is actually the power in inertial frame of reference. And this is the power in the body fixed frame of reference. Right? And we basically know from kinematics, the relation between eta dot and zeta. Right? Eta dot is nothing but x dot, y dot, psi dot, the velocity coordinates with respect to the inertial frame of reference. And zeta is nothing but u, v, and r, the velocity coordinates with respect to the body fixed frame of reference. And we also have from dynamics, just the thing that we have just derived from dynamics, we have this torque tau as b multiplied by zeta dot plus n of zeta. Right? So I'll call this equation as equation 1. I'll call this as equation 2. I'll call this as equation 3, because equation 3 is what we derived earlier, actually, from Newton-Euler formulation or from Euler-Lagrange formulation. Right? So yeah, So we have this term zeta dot over here, right? But from kinematics, we only have this term zeta. So to get zeta dot, we'll take the derivative of equation 2. We do so by this, differentiating equation 2 with respect to time. We'll have to apply the product rule. So eta double dot is nothing but j dot of psi multiplied by theta plus j of psi multiplied by theta dot, right? So from here, you can find out zeta dot as eta double dot minus j dot of theta, j dot of psi multiplied by theta. Yeah, and you have to pre-multiply this with j of psi inverse. This is the expression for theta dot. So I'll label this as equation 4, right? And I back substitute this equation 4, right, onto equation 3, right? Instead of the theta dot, I'll substitute, what we have obtained from equation 4. So equation 4 in equation 3, we will get tau as d multiplied by j of psi inverse eta double dot minus j dot of psi theta plus n of theta. So I'll call this as equation 5. All right, that is our tau. Okay, now what else can we do? Now, we can basically compare these two equations. So we'll keep this apart. We'll keep this equation 5 apart for the time being. And now, if you consider this, if you substitute equation 2, onto equation 1, instead of this eta dot, I'll substitute eta dot as j of psi multiplied by theta. So substituting 2 in 1, you will get tau eta, that is the torque or the French vector in inertial frame of reference, tau eta transpose j of psi multiplied by theta is nothing but tau transpose zeta. So these thetas will get cancelled. So at the end, you will end up with tau eta transpose j of psi is nothing but tau transpose. So if you take the transpose, of this entire equation, taking transpose, you will get it as j of psi transpose tau eta. This is nothing but tau. So I label this as equation 6. So if you go back to equation 5 over here, instead of this tau, I substitute this term, this equation onto equation 5. So 6 in 5, we will get it as j of psi transpose tau eta. This is nothing but d j of psi inverse eta double dot minus j dot of psi zeta plus n of theta. And if I, bring this term over to the other side of this equality, you will get it as tau eta is j of psi inverse transpose D J of psi inverse eta double dot minus J dot of psi theta plus J of psi inverse transpose N of theta. That's how it is. You know, since we also know for a fact that this J of theta or J of psi is it's a rotation matrix. A rotation matrix is also an orthonormal matrix. So the inverse of that matrix is its transpose, or transpose is also its inverse. So essentially, we are taking the transpose here twice, or we are taking the inverse here twice. So that cancels itself. So I can write this as tau of eta as j of psi multiplied by d and j of psi. Instead of inverse, I prefer to write it as transpose. Then if I expand it, I'll get it as eta double dot minus j of psi d j of psi transpose j dot of psi zeta plus j of psi multiplied by n of theta. So this is our equations of motion in inertial frame of reference, right? And we all know that the coefficient of this acceleration vector is our mass matrix, right? Just like we have seen earlier. So this eta double dot is our acceleration vector, and the coefficient of eta double dot is basically this term, right? So I'll write that mass matrix D of eta as J of psi D J of psi transpose. This is our mass matrix in inertial frame of reference with respect to inertial frame of reference. This was our mass matrix on body fixed frame of reference, and this is the mass matrix with respect to the inertial frame of reference. Okay, so that's how you translate or transpose the equations of motion from body fixed frame of reference to the inertial frame of reference. And another small aspect that I would like to consider is the dynamic wheel configuration matrices for different wheel configurations. So like if you have gone through this kinematics, we have this wheel configuration matrix for different architectures. The different architectures were, we had this differential wheel drive, we had this mecanum wheel, we had this skid steering, we had this omni drive, where we related the velocities of the body fixed frame of references, UVR, to the angular velocities of the wheels, omega 1 and omega 2, so on and so forth. Here we do something equivalent, or we do something analogous or similar. We transpose this Fx, Fy, and Mz to the individual tractive forces on each of these wheels, F1 and F2. Right? Because we basically derived this from the equations of motion. And then we would like to know, how does that translate to the traction force on each of these wheels, F1 and F2. And doing so in this, this is actually much more simple, because what you have to do is you have to only consider the equilibrium with respect to x-axis, y-axis, and the moment equilibrium about z-axis, right? So if you consider the net force along x-axis, it's not equilibrium, net force along x-axis, Fx is nothing but F1 plus F2. That is what we have written here. And so Fy, no net force is acting on the wheels along Fy. So that makes it Fy as 0, right? And moment, Mz is nothing but, the moment contributed by F1 with respect to on this point of axis. Yeah, I've got a clarification. Mz is F2 minus F1. Is it so? So yeah, F1 actually makes a clockwise moment. So that makes it minus F1B, and F2 makes it a counterclockwise moment. So that makes it F2 multiplied by D. So that makes it F2 minus F1 into D. Yeah, that's correct. What you pointed out is indeed correct. So this is, I'll just scratch it off. The correct expression is F2 minus F1 multiplied by D. And you can write all these three equations as a matrix and a vector form, like so, right? Like so. Then the three scalar equations written in a vector and matrix form. So a similar thing can be done for the omni wheels. You know, if this is the omni wheel, like this, we have passive rollers, right? Passive rollers like this. You know, these are free to roll, you know, in these directions, and these are free to roll in this direction. And the tractive forces act along the direction of the main periphery of the main wheel. F1 would be like this, F2 would be like this, F3 would be like this, right? And the forces, you know, Fx along x-axis, Fy along y-axis, and Mz along the zb axis. You have to resolve all these forces along x, y, and z, right? So if the angle between F1 and this x-axis is phi1, I'll label this as phi1. And if I label this angle as phi2, and I label this angle as phi3, you know, the angle each of these forces makes with respect to xb axis, you know, the component of F1, F2, and F3 along x-axis is F1 cos phi1, F2 cos phi2, F3 cos phi3. And the y components are nothing but F1 sin phi1, F1, F2 sin phi2, and F3 sin phi3. And the moment is nothing but force multiplied by this perpendicular distance, right? This perpendicular distance, you can consider the radius to be L. So this is F1 multiplied by L. So that acts in a counterclockwise direction. So that makes it plus F1 multiplied by L. This is also counterclockwise. F2 multiplied by this radius, and this is F3 multiplied by this radius, right? Yeah, you can write these three scalar equations as a matrix and vector form, like so. And as you can see, you know, F1 is actually 90 degrees. So phi1 is nothing but 90 degrees. And phi2 is, you know, the orientation between wheel 1 and wheel 2 is 180 degrees apart. We already have a 90 degrees for wheel 1. So the phi2 would be 90 plus 120. This is 210. And phi3 is, you know, 210, or, you know, you can write it as, with respect to 1, you can call it as 90 plus 210. This is nothing but 330 degrees, phi3. And you can substitute the numerical values here, and you will get the corresponding numerical matrix. This is one more case. You know, it's like a tricycle, right? The front wheel is actually powered, and it's also steerable, right? You can actively control the orientation of this wheel using this variable theta. You can also drive this wheel using an independent motor, which would impart this tractive force F1. So then what are the net forces along x-axis, y-axis, and the moment about z-axis? So if you resolve this force along x-axis, this is nothing but Fx is nothing but F1 cos theta 1, and Fy would be F1 sin theta 1, and Mz would be F1 sin theta 1 multiplied by this L, length L, right? But if you look at here, we have written it as Fy as 0, right? And the reason is that even if there is a component, even if there is a component of F1 along the vertical direction, these are actually conventional wheels. These are basically passive wheels, and they impart infinite resistance along the lateral direction, right? So no matter how much effort this F1 has along this lateral direction, along YB axis, due to this infinite resistance, this will get cancelled, this will get suppressed. So the net effect would be zero. Net effect would be zero, right? Because, if you can imagine, if this wheel was in fully vertical direction, and if you're trying to drive it, this won't move, right? Because these wheel will provide infinite resistance, and as a result, it cannot slide in this direction. And as a result, we consider this Fy to be zero, the net force along Fy to be zero, because these are conventional wheels and they provide infinite resistance in the lateral direction. And the final case, we have this, the mechanism wheels, where F1, F2, F3, F4 are all acting at an angle because of these passive rollers. So F1 would probably act like this, F2 would act like this, F3 would act like this, and F4 would act like this, right? And if you resolve all these forces, F1, uh, F2, F3, F4 along x-axis, y-axis, and if you resolve all the moments about ZB axis, you will get these components. And theta 1, theta 2, theta 3, theta 4, as you know, these are all plus 45, minus 45, plus 45, minus 45 degrees in typical examples. That's how you get these values. All right. So with that, we'll move on to some sample problems that you can expect during this assignments. So, okay, the first question is for a given input vector, calculating the resultant motion of the robot, that is eta dot, eta dot, and eta double dot is known as, what is this process called? So we know that, if it has something to do with the forces and torques, the answer should be something related to dynamics. It could be either forward dynamics or inverse dynamics, right? So if you have a robotic system, and if you give an input vector tau, you are basically expecting the robot to behave in a particular way, or you are expecting the state of the robot to change, which are characterized by the position, velocity, and acceleration. So this process, supplying a torque vector and observing what the robot does is actually the process of forward dynamics, right? It's like simulating, or it's like simulating or analyzing the mobile robot. Give an input, see what the robot does. So I hope that's clear. The answer is option C. Now moving on to question 2. The Lagrangian L is equal to, we have seen how we define the Lagrangian for a mobile robot. It's a scalar quantity. It's nothing but the difference between the kinetic energy and the potential energy. And we use this Lagrangian to derive the equations of motion. So by definition, Lagrangian is nothing but the difference between kinetic energy and potential energy. So that's equation, that's option B. And for option question 3, given a differential wheel mobile robot, okay, so I'll just draw a differential wheel mobile robot like so. So yeah, these are the two wheels. And I'll attach a body fixed frame of reference like so. This is XB, this is YB. And sticking to the convention of our course, I'll label this as, like wheel 1, this is wheel 2. We'll mark this direction as the longitudinal direction, and we'll mark this direction as lateral direction. And also we'll consider this side, wheel 1 to be the left side and wheel 2 to be the right side. So if that is the case, what are the things given in the question? It says the first wheel is generating a traction force of 1 Newton, and the second wheel is generating a traction force of 2 Newtons. Then what will be the forward and lateral direction forces? So Fx is nothing but, you simply take the force balance. Fx is nothing but 1 Newton plus 2 Newton, that is nothing but 3 Newton. And Fy is essentially 0, right? Because, we only have forces along this direction. And we always know that conventional wheels have infinite resistance along the lateral direction. So Fy is 0. So that makes our answer to be 3 Newton and 0 Newton. So I think the answer is option C. This is the forward for forces in the forward direction. And this is the forces in the lateral direction. I hope that is clear. If there are any doubts, please feel free to interrupt me and let me know if if further clarifications are required. So again, a similar question for a differential wheel mobile robot. If the first or if the left wheel is generating a traction force of 1 Newton and the second wheel is generating a traction force of 2 Newtons, then what will be the vehicle's motion? I mean, from pure intuition, you can see that, this wheel has more force than this wheel. So from intuition, you can actually see that the robot is going to move in like so. And it's going to take a curved path like this, right? So the way you can characterize this, it'll move forward. This is obviously false. Move backward, that is false. Moving forward is correct though, right? Because it basically moves in the forward direction. But is that the most correct option? Yeah, I've got it as option 3. Move forward and rotate in a counterclockwise direction. That is indeed correct. Yeah, move forward and rotate in a counterclockwise direction. So I don't think we need to linger more on that. It's fairly obvious. Moving on to question 5. For a given mechanism wheel drive, the wheel configuration matrix in the dynamic level can be written as follows, so and so. So if the vehicle needs to move in the lateral direction towards right, then what will be the individual wheel forces? How do we solve this? We have to find the right combination of F1, F2, F3, F4. Right? So if we have a mobile robot base like this, and if these are the body fixed frame of reference, XB and YB, and we expect the robot to move in the lateral direction towards right. So this is the lateral direction. And by convention, we'll keep this as the left side and we'll keep this as the right side. Right? So if the robot has to move along the right side, how would Fx, Fy, and Mz, how should it look like? Right? It should move in the right direction. It should move towards the right direction. So it should not have any net force along x direction, right? So Fx should be 0 Fy should be some negative constant, right? Because right side is actually aligned in the negative YB axis. So the Fy should be a negative value and Fz should be 0 because we do not expect any rotation about ZB axis. So if it has to move along the right side, this is how our Fx, Fy, Mz vector should look like. And which of the combinations of F1, F2, F3, F4 will give you this vector. So I'll simply reproduce this wheel configuration matrix 1 by root 2, then 1, 1, 1, 1, 1 minus 1, 1 minus 1, L minus D, L minus D, minus L minus D, minus L minus D. We'll see a couple of options. What about this one? F1 is all the forces are acting in the positive direction and all of them have equal magnitudes. So it should be fairly obvious that if all the wheels have the same magnitude and if they are all in the same direction, the robot should move forward in the fx direction, right, along the longitudinal direction. And the second so we can fairly eliminate that because that is not what we want. The second option is it's F minus F minus F, right? So the first two forces act along positive direction, and the second and the third and the fourth act in the negative direction. So again, it should be fairly obvious that if we have this sort of configuration, the mobile robot would rotate like this, in the clockwise sense, right? Two wheels going in this direction, two wheels going in this opposite direction. So the mobile robot would rotate like this. So we can also eliminate that option based on intuition. And what about the third option? It's minus F minus F. So we really do not know how it would behave. So let's try that option. Minus F. Sorry. Let's try that option. Minus F minus F. So if I multiply this matrix and this vector out, what will you get? I'll just write it over here. The first entry would be, minus F plus F minus F plus F. First entry is going to be 0. The second entry is minus F minus F minus F and minus F. So it's actually minus 4F. And the third entry is this is a positive quantity. This is minus F into L minus D. This is plus F into L minus D. Those two get cancelled. This is plus F into L minus D. This is minus F into L minus D. So that is also 0, I suppose. All get cancelled. So yeah, in that case, this looks like a potential candidate, right? It's a negative quantity, and that is what we expect. We expect the second entry to be a negative quantity. So in that regard, we can fairly agree that option C is the correct answer, right? Because it only has a component along Fy axis and that too along negative Fy axis. And that is exactly what we want, right? The question expects the mobile robot to move along the right side, and the right side is basically aligned along the negative YB axis. So we have Fy, we expect Fy to be a negative quantity and all the other quantities to be zeros. So we can probably agree that option C is the correct answer. So that is indeed correct. So I hope that is clear enough. So moving on to question 6. The inertia matrix of a mobile robot with respect to the body frame is given as so and so. So the inertial matrix with respect to body frame is given as 10, 0, 0.5, 0, 10, 0.1, 0.5, 0.1, and 1. If the vehicle is oriented 60 degrees with respect to the inertial frame, what will be the inertia matrix with respect to the inertial frame? So you have this inertial frame of reference attached to the ground. This is inertial frame of reference, xi, yi, and the mobile robot is oriented 60 degrees. This is xb, this is yb, and this relative orientation, this is 60 degrees. And if you can recall from the previous slides, we have derived the relationship between the inertial matrix in inertial frame of reference and the inertial matrix with respect to the body frame of reference, right? That is nothing but what was that expression? J B J transpose. So I'll write this way. We derive this expression from the conservation of power, J of 60, P of theta, J of 60 transpose, right? This J is nothing but the rotation matrix that that accommodates this orientation between frame B and frame I, right? So if you put the numerical values, it will be like cos 60 minus sine 60, 0, sine 60, cos 60, 0, then 0, 0, 1. Then you multiply this out with the inertia, the mass matrix, 0, 10, 0, 0.5, 0, 10, 0.1, then 0.5, 0.1, 1. Then multiplied with J transpose. That is cos 60 minus sine 60 is 0, sine 60, cos 60, 0, then 0, 0. So if you multiply this out, you will get the value for the mass matrix with respect to the inertial frame of reference. So yeah, I would give the answer straight away. The answer would be, I believe it's option B. If you expand this out, you will get the numerical result as option B. Right? If you want to know about how we got this expression, I would recommend you to go back to the previous slides. The recordings and the PPTs will be shared after this session. We derived this expression from the conservation of power, and that's how we got the relationship between the mass matrix of on inertial frame and mass matrix on uh, body frame of reference. Yeah, that is indeed the solution. Going back to the second last question of this today's session, it's almost similar to the things that we have solved earlier. So given a three-wheeled Omni drive, the wheel configuration matrix in dynamic level can be written as follows, so and so. So I'll just have a quick overview of the Omni wheel drive. So these are separated 120 degrees apart. And we have the three wheels. This is wheel 1. This is wheel 2. This is wheel 3. We label this as wheel 1, wheel 2, wheel 3. and this is the xb axis. This is the yb axis. Okay, now we'll continue with the question. If the vehicle needs to move in the negative lateral direction towards the right, then what would be the individual wheel forces? Again, the objective is still the same. It should move along this direction, right? So this is left, this is right, right? So if it has to move along the right direction or along the rightward direction, how should the vector fx, fy, mz, how should it look like? So fx, fy, mz for rightward motion should look like this: 0 minus k 0, right? It's a pure motion along the rightward direction. It should not move along x direction, and it should also not rotate. So which of these combinations of f's would give you the rightward motion, or which would give you this motion, right? So how do we do that? So I'll reproduce that wheel configuration matrix: 0 minus root 3 by 2, root 3 by 2, 1 minus 1 by 2, minus 1 by 2, L, L, L. So if you take a look at the first option, it says F, all the forces are acting F in the positive direction, and all of them are of equal magnitude. So if that is the case, it would look something like this. This is F1, this is F2, this is F3. If this is the case, the mobile base would rotate like this, in the counterclockwise direction. So that is not what we want. We want it to move rightward. So we can eliminate that first option. What about the second option? The second option says F1 is F, F2 is F, F3 is minus F. This is F, this is F, and this is minus F. Right? If you do that, what will it happen? F, F, minus F. So if I expand this out, what will you get? You will get it as 0 minus root 3 by 2f. So the first term is actually 0. The second term is f minus f by 2 plus f by 2 minus f by 2 plus f by 2. And the third term would look like fl plus fl plus fl. So this would turn out to be 0, 0f and 3fl. I hope I'm correct. F minus f by 2 plus f by 2. I hope I'm correct on that. So, this is our fx, fy, mz vector. And this is not what we want, right? That is not what we want. So we can also eliminate that option. Second option we can eliminate. And as a result, third option does not look very encouraging. Third and fourth option also does not look very encouraging, because they are also similar. And it will always have some component along the MZ direction. So we'll do one thing. We'll just try one of the final two options. We'll try either of these two options. 2f minus f and minus f. Let's try that. 2f minus f and minus f. So if I expand that out, I will get it as the first entry would be plus term and minus term, that would be 0. And the second entry would be 2f. Then you will get plus f by 2 plus f by 2. And the third entry would be 2fl minus fl minus fl. So this is 0, 3f, and 0. So this is somewhat similar to what we are looking for, but not exactly equal, right? Because here this is a positive quantity, but we expect to have a negative quantity because we want the robot to move along the negative YB axis. Right? So we are nearly getting there. So I think we tried this option. Now we'll try this option, right? It looks more or less similar, but the signs are really flipped. So if you try that option, instead of the fifth option, if you try the sixth option, let me check that. If it is minus 2f, f and f. If you expand this, the first entry would be 0. The second entry would be minus 2f, minus f by 2, minus f by 2. And the third entry would be minus 2fl plus fl plus fl. So this would look something like 0 minus 3f. Third entry would be 0. Now you can see, this is similar to what we actually want, similar to what we expect. So in that regard, we can fairly say that the final option C, D, E, F, F is the correct answer. Right? So I hope I made myself clear with that. The option is indeed option F. Now we'll go to the final question, one final question for this session. So it says the vector of applied forces and torques with respect to the body fixed frame of reference, tau is given as 537. Right? Then what is the vector of applied forces and moments with respect to the inertial frame of reference? Right? So if your body frame of reference is given as xb and yb, and this inertial frame of reference is somewhere here, xi and yi, and this tau is nothing but the forces and moments about the body fixed frame of reference, fx, fi, mz. You are asked to find out this tau eta, with respect to the inertial frame of reference. How do you do that? And it's also given that the x-axis of the frame B is 30 degrees with respect to the x-axis of frame I. So the relative orientation between the two frames is, I may have to redraw this a bit. If I call this as xb, if this is yb, and the relative orientation between both of these frames is 30 degrees, then you are asked to find out tau eta. The way to do this is, from this conservation of power, the power consumed in both of the frame of references is equal because it's a scalar quantity. So tau eta transpose multiplied by eta dot. This is the wrench in inertial frame. This is the velocities in inertial frame. And this entire term is the power. This is nothing but tau transpose multiplied by theta. This is the wrench in B frame, and this is the velocities in B frame, right? And but from kinematics, you know that eta dot is J of psi multiplied by theta, right? So if you substitute this equation to here, you will get tau eta transpose J of psi multiplied by theta as tau transpose theta. So these terms will get cancelled. And if you take the transpose of this entire equation, you will get J of psi transpose tau, or I'll bring this Jacobian matrix to the other side. Or rather, I'll just take the transpose first. So J of psi transpose tau of theta is nothing but tau. And to find this, you are asked to find out this tau of eta. So you have to, bring this Jacobian matrix to the other side. So if you bring it to the other side, you have to take the inverse of this to the other side. So inverse and transpose are basically the same for a rotation matrix. So this would in turn result to tau eta as J of psi multiplied by tau. So J of psi, you can basically assemble the Jacobian matrix, because the orientation is 30 degrees, cos 30 minus sine 30, 0, sine 30, cos 30, 0, then 0, 0, 1. Then tau is given in the question as 537. And if you multiply this out, you can find out the answer, which turns out to be, I think it's option B, 2.83, 5.09, and 7. Turns out to be option B. Yeah, that's indeed the correct answer. Yeah, so with this, we can wind up today's session. I guess we have covered all the questions, all the kind of questions that you can expect for, the week 3 quiz. If you can master what we have covered in this session, you can probably, go through the quizzes very easily. So with that, I think we have also covered 2 hours for this session. With that, I would like to wind up this session, unless there are any more questions. Are there any more questions? Okay, so thank you for joining. With that, I will wrap the session up. Thank you for joining, and see you next week.